All right. Yep. I think we've started. Kira, good evening, good morning, afternoon to everyone. Thanks for joining our research training group. So today we have Dr. Ackley, who will be making a presentation on IEQ in schools. Welcome, Ackley. I'll just pass it up to you.
Thanks very much, Dr. Wallace. Warm greetings to all. It's a great pleasure to share with you today an aspect of architecture that I'm very passionate of, and which is the impact of indoor environmental quality on health and energy efficiency designs of buildings. As I walk through the slides, I will refer to indoor environmental quality as IEQ. This seminar will cover the impact of IEQ on users of this building. It will also cover the mechanisms that are behind the element of IEQ. It will also cover the measurement, the ways or methods we could use to measure IEQ in distant buildings. Cool, so I will begin with a bit about myself. My background is in architecture, and in the last few years, I've led and carried out many research projects on improving indoor environment. I will try to make this seminar to be as engaging as possible so that I'm not the only one that will be talking through the next few minutes or hours. To begin with, I thought it would be great to have a simple quiz where there is no right or wrong answer. And we are going to use Mentimeter for this quiz. So if you could get your phones and laptops ready, and I will share the link to the chat room. And all you just need to do is to click on it to answer very simple questions. I think we've got someone in the chat room. Admit. Cool. So I will just minimize this screen and share the next screen, just trying to stop presenting. So our first quiz, where are you? Yep. I will present this and copy the link, and I'm going to put this in the chat room. We could just click on that link and answer the question of what goes in and around the building but never touches it. Just click on the link in the chat room. We just allow 3 to 4 more seconds. Awesome, it seems everyone has sent through the answers. Cool, okay, more answers are coming in. Maybe we'll just allow another 15 seconds. Looks good, so we will move to the second quiz. Just trying to minimize this. The second brain teaser. Present. And I'm going to put another link in the chat room, and you just click on it and share your thoughts. I've just put another link in the chat room for the question on what goes in and passes through a building and is felt by the occupants. We'll allow another 15 seconds to see if we have more people Remember, there is no right or wrong answer. The link is on the chat room. Just click on it and you can answer the question from there. Okay. Well done to everyone for sending through your answers. I'll just share my slides again and we'll crack on from there. Just sharing my slides. So we can see from this image we've got on the screen that the sun rises from the east and the sun sets in the west. And the sun goes in and around a building to illuminate it as it makes the journey through the building. Also, we can see that the wind passes through a building, and depending on the configuration of the window, it creates a cross flow of air. And in summary, we can see that the sun and the wind are two key things that either brings in light to a building or brings in heat to a building, either cools or warms the building. And also the wind also helps to either brings in ventilation to that building. This takes us to the definition of IEQ. IEQ refers to the conditions inside the building that promotes the comfort, the health, and the well-being of the users of that building. There is a growing number of studies that have shown that daylight, thermal comfort, ventilation, and also indoor air quality, as well as acoustics, are the 4 key elements that impact on the quality of the indoor environment. In homes, good daylight could improve one's mood. Ventilation is about helping fresh air to circulate through your home, just like we've seen from the pop quiz that we've just had about what goes in and through a building and is felt by those who use that building. It also allows moisture and airborne pollutants to escape and fresh, clean air to be drawn into your home. Well-designed ventilation will provide cooling in winter, cooling in summer, and then in winter, it will let stale air out while minimizing heat loss. For acoustics, and when outside noise pollution is too great, it can have considerable effect on how well people will sleep in a building. In schools and offices, performance can decrease if the lighting is too bright or dark. The temperature is too cold or warm. The noise levels make speech too hard to hear, or poor ventilation makes the air too stuffy, with high levels of carbon dioxide affecting the ability to concentrate, as shown in the image from the Asthma and Allergic Foundation of America. The influence of these variables on performance are robust, even when statistically controlling for other factors. For example, a daylight study by Heshon showed that even with the analysis of the teacher characteristics, student absenteeism data, and grade level variables, the daylight element stayed highly significant as a factor that impacts learning. In their teacher survey analysis, thermal and visual comfort, acoustic and adequate ventilation were all frequently listed as top priorities. If you attend, let's say, a 3-hour workshop in a conference room, and that room doesn't have natural ventilation and daylight, let's say the room is in a basement, and you've got many people inside that room, have you ever wondered why you may feel dizzy after about 30 minutes or maybe 45 minutes into the meeting. The phenomenon is that when you have many people inside an enclosed space, after a while, the CO2 level rises because we breathe out CO2. And high CO2 levels have been associated with a reduction in cognitive performance because it reduces your attention span. Good daylighting has been shown to improve the overall attitude, satisfaction, and well-being of building occupants. It can suppress melatonin production, which improves alertness. You'll find out that if you've got a room that faces the east, being that the sun rises from the east, as we saw in the first three slides, and sets in the west, depending on the time the sun comes up, if the sun comes up maybe like in the summer here, the sun could be up from around 7 or 8. You find out that if that sunlight, it actually penetrates deep into your room, you may not be able to sleep again. And this is due to the fact that what it does, it suppresses melatonin, which is produced in our body, and it helps us to sleep at night when we don't have daylight. Also, a daylight study by Hessian showed that students with the most daylight in their classrooms were found to progress 20% faster on math test and 26% faster on reading test over the course of a year. When we calculate the time people spend in indoor spaces, let's say 8 hours of sleeping in your room and another 8 hours in the office or school. This makes it important to ensure that these indoor environments have quality indoor spaces. Good IEQ in buildings would lead to long-term energy efficiency. For example, not only does daylight replace the use of electric lighting during the daytime, reducing energy use for lighting, it also influences both heating and cooling loads, which makes it an important parameter of an energy efficient design. With good design, you can use windows, you can use vents, you can use other openings for most ventilation. These will also help to save your energy costs. The proper placement of a building in terms of being able to control for the solar gains during the cooling periods can be mitigated, and the solar gains during the periods, during the cold seasons, could be used to actually warm up the space, thereby reducing the energy requirement of both cooling and heating a space. With the insights of the impact of IEQ on performance and health, we would briefly have another short quiz before we move further. I will just share my Mentimeter again, and we'll have another pop quiz, which is the third pop quiz. There we go, brain teaser. Present screen, and copy link, and I'll put this in the chat room. So with what we've just talked about, the various factors that impact IEQ, click on the link in the chat room, and could you rate which of the IEQ elements do you think is most important? We'll allow another 20 seconds. Click on the link in the chat room, and could you rate? Remember, there is no wrong or right answer. Which of the IEQ factors is more important? We'll allow another 10 seconds, and then I would share my slides again, and we would Crack on. Thank you for your answers. Thank you. Okay. Just about sharing my slides again. As shown in the quiz, there are many schools of thoughts on which IEQ element is most important. Depending on the experts you have in the room, the acoustician will tell you that acoustics is the most important. On the other hand, the lighting engineer will say that lighting is the most important. But the bar chart we have on the screen shows the relative importance of each IEQ element in different settings, from offices to schools to homes. The goal was to consider how important each element is relative to the other factors, and to ascertain whether there is a consensus among researchers in offices that differs from the ones in homes or the ones in schools. Though thermal quality appears to be ranked in some settings, the result is not convincing to conclude that thermal quality is the most important IEQ factor. The overall trends indicates that there is no consensus on the importance of each IEQ element relative to the other factors. Hence the need to consider these elements holistically, because depending on the setting, is it an office space, or is it a residential building, a healthcare facility, or a school, a change in one factor could affect the other. Moving on. When designing for IEQ, the following factors should be taken into account. The orientation of the building. Is it going to be a north-south facing orientation? Is it going to be an east-west facing? And bearing in mind that as you make this choice, you're relating it back to what passes through a building and is felt by those who use the building in terms of the wind. And depending on the part of the wall you are in, you may want to trap the southwest like this prevailing wind if you're in Nigeria. And if you're in another side of the wall, in the northern or in the southern hemisphere, you may want to place your building in a way where it is possible for you to trap the wind that will not just be a wind that would make it very difficult for the windows to be used, but a wind that I will call it good wind that will provide the cross flow of air. Aside from that, the other things you need to think about is the type of glazing. You need to think about those who use the space. So you cannot talk about good IEQ without an understanding of the functions of that space. Is it going to be a school building? Is it going to be a restaurant? Is it going to be a cafe? You need to think about the end users of that space. You need to think about reflectivity of the various surfaces in that space. You also need to think about the acoustics of that space. We will be drilling into most of all of this as we go through the various factors that impact IEQ. We'll begin with an overview of lighting. Daylighting is the act of lighting the interior or exterior of a building with natural light. Daylight is a vital environmental factor that largely defines the quality of the indoor environment because it is associated with the visual and energy efficiency design of a building. Successful daylighting requires design considerations at the early stages of the building design process, from site planning to architectural to the interior and till when you're doing work on the lighting design of that space. Daylighting in buildings is composed of a mix of the direct sunlight, diffuse light, and light reflected from the ground and surrounding elements, and needs to consider orientation, the characteristics of the site, the facade and the roof, the characteristics of the roof, the size and the placement of windows, the glazing, the shading, the geometry, and the reflectance of interior surfaces. When designing for daylight, direct sunlight and overglazing should be avoided because it can cause visual discomfort. Solar heat gain can cause thermal discomfort, glare, deterioration of the facade of the carpet, of the fabrics of equipment because of its high UV light content. Overglazing can create excessive solar heat gain in summer and a major heat loss during the cold season. Practical methods for excluding this direct sunlight includes the use of shading strategies. It includes the use of blinds where this is needed. It also includes the correct orientation of the window, being that your aim is to be able to trap what goes in and around the house in a way that is not going to lead to either excessive heat or lead to excessive glare inside the space. On the other hand, to avoid overglazing, you need to consider all the factors that we've described to be able to avoid a direct sunlight. And then you go further to think about the size of your windows. You now need to think about how you're going to control any solar heat gain from the type of glass that will be used in that space. Depending on the design, window design could help in optimizing daylighting. Roof lights could help to admit light from the brightest part of the sky. It can provide a more even distribution of light across a space. It could allow you to see the sky, but need careful design to avoid direct sunlight and solar heat gain. You recall the slide 3 when we did the brain teaser where we had the sun rising from the east and setting in the west. You found out that if you've got a roof light, there is a potential that when the sun is at noon, very high, there could be a potential for high solar rays penetrating into the space, which is where you now need to think about, if you're using a roof light, how are you going to block out any potential for excessive glare? The advantages of clerestoral windows are that they are high up, and so it lets light from the bright part of the sky. They are unlikely to be obstructed by trees or other surrounding structures, can provide light to the darker part of your room. It can also give you some idea of what it's like outside, and it can also provide extra ventilation. Glare is an important thing to think about when designing for daylight. Glare is caused by overly bright light contrast. It is a subjective sensation that describes light within the field of vision that is brighter than the brightness of which the human eyes can adapt to. Typical situations to avoid include where the direct sunlight falls on or near a tax areas. There is high contrast between the windows and the window frames or the adjacent walls, and the sky can be seen through the roof light at a viewing angle of less than about, I think, 35 degrees. The table shows illuminance-based dismetrics for assessing daylight quality in buildings. Historically, daylight factors and a uniform overcast sky have been used to determine the quantity of daylight available within a room. This conservative method was suited for places which have a greater proportion of overcast skies. This approach does not, however, consider the effect of direct sunlight or of varying illuminance over time. Building designs which maximize daylight factors have resulted in oversized glazing with detrimental effects in terms of thermal control and glare, which led to the climate-based illuminance dismetrics that we've got on here, where we are saying if you use a climate-based dismetrics of the UDIs, the daylight autonomy, this would be very able to account for any areas of excessive light and eliminate glare, and also have a lower threshold where it is not too dark and it is not also too bright, and uses the local weather data of a particular city or place to carry out an estimation or verification of whether a space will meet the daylight targets or levels. We're going to watch a small video, a short video to wrap up the things we've just talked through so far on daylighting. Fingers crossed, I hope the audio plays. Just wondering if you can hear that, please. I will play it again and you just let me know if you can hear the audio, please. Can you hear the audio?
No, we cannot hear. I think you need to share your computer audio.
Yep, so I'm just going to say stop recording. Meeting info. Is that under more, right?
Yes.
Yeah,
so. More options.
Yeah, I think I've just done. So I'm just going to try it again, and you let me know if you can hear it, please.
Okay,
yes,
so we all know that.
It now.
Sweet. Okay, I'll just start from the beginning. So this is just a short 2.44 seconds, 2 minutes and 44 seconds video that will actually help to wrap up all of what we've just talked through in the last 4 to 5 slides.
Okay, so we all know that windows can provide a great view, right? But if they're placed in the right locations, they can also save you money on your utility bill. And they can help keep you more comfortable at home or work. It's called daylighting, and it takes a simple concept to a new level. Daylighting combines lots of things. Everything from the type of window, window placement, and interior design to control how sunlight comes in. They all work to maximize benefits from natural sunlight. Check this out. Windows that face south are best in the US. They let in the most light in the winter months, but little direct sun during the summer, keeping the inside cooler. North-facing windows are also good for daylighting. They let in even natural light with little glare and little summer heat. Windows that face east and west don't work nearly as well for daylighting. They do provide lots of light in the morning and afternoon, but it often comes with lots of glare and excess heat during the summer months. Have a look at this energy-efficient office building. The windows team up with skylights to provide most of the light you need. Notice the light color of the ceiling. It reflects and enhances the daylight so that it fills the room. And what about all the overhead lights? Most of the time, you don't need them. To account for glare, this office building placed hoods outside around the windows. The hoods also cut down on summer heat, keeping the office cooler and more comfortable. On the inside, louvers or tinting reduce glare and also direct light to reflective surfaces inside, allowing plenty of natural light to come into work areas. One big help to daylighting is the window technologies available today. Windows are now way more energy efficient. They insulate while still letting the light you want in. And have a look at this. It's an electrochromic window. This special window changes with the brightness of the sunlight outside. As the sun tracks across the sky, it darkens to keep excess heat out. It's like giant polarized sunglasses. Daylighting can have a positive effect. Studies have shown that with good daylighting at the office, productivity goes up and absenteeism goes down. And that's good for the bottom line. Natural lighting and heating means you use less electricity and lower your utility bill. And the more natural lighting, the more money you can save.
the key things to note from that video is that west and east facing windows could be prone to glare issues. And this is due to the low angle of the sun in the mornings and also in the late afternoons. So when designing your windows on these orientations, the strategies such as using a window hood or trying to look for ways to shade could be helpful to optimize daylighting. Also, the video showed us about the use of electric chrome windows, which is an emerging technology for regulating the amount of light admitted into a space depending on the intensity of the sun at a point in time. The artificial lighting in the office building we saw in the video was switched off due to the use of daylighting, which could help in lowering the electric bills of that office building in the long term. I will just go back to my slides and then we would continue from there. Sorry about that. Just need to reshare it and we'll move on to thermal comfort. Thermal comfort is the condition of mind that expresses satisfaction with the thermal environment and is impacted by factors such as age, such as gender, such as the insulation level of the clothing which one is wearing. And studies have found that children are more capable of coping with colder temperatures than adults. Children are more sensitive to higher temperature levels than when the temperature is at the colder end of the spectrum. A study by Kozavic 2020 suggests that children's thermal their comfort is about 3 degrees lower than that for adults during non-heating and heating seasons. Achieving good thermal design is linked to achieving good day lighting and also achieving good ventilation in a space, as well as achieving good insulation in your walls, in your floors, and in the roof. This again shows the interrelatedness of daylighting to achieving good thermal comfort in buildings. Moving on to acoustics. Building acoustics is the method by which noise is controlled within a building. This includes the measures in which to reduce noise when it's necessary, and also how to ensure effective transmission of sounds through a particular space. Wall insulation, and I will also say the floor insulations, and then the roof or this is ceiling, could help to reduce surrounding noise from reaching inside of a building, but also it could also help to make a building to be more energy efficient. These features can help to reduce the escape of heat from a building, making the spaces within it stay warmer for longer and reducing the need to generate as much heat. Again, this shows the link between the solutions for achieving good acoustics, tying it to that of the thermal comfort, how they are all linked, and a change in one could impact the other. Indoor air quality is a broad area that looks into different types of air pollution, including particulate matter and VOCs. As you may already know, ventilation has been recognized by the WHO as one of the ways of mitigating the spread of SARS-CoV-19, which means that it is important for us to ensure good indoor air quality. And I think the signs that we have seen of this in recent shows that if you have good cross flow of air, it could minimize the spread of this virus, and it could help to minimize the transfer of it from one place to the other. Cross ventilation is one of the best ways of achieving good ventilation. Where needed, it's possible to use a mixed mode system, or you could also use a mechanical system, more like a last resort, where natural ventilation is not effective. These methods of ventilation will not only achieve good air quality, but it will help to minimize energy consumption. There are a couple of ways to measure and ascertain good IEQ, both at the design stage and after a building has been built. For example, during the concept stages of this design, careful consideration of the building form, the orientation, similar to what we saw in slide 3, and the glazing area are things that are useful in getting started with designing for good IEQ. Simulation software such as Rhino, IES can be used at the preliminary design stages to check whether the building will have good or poor IEQ. And post-construction, you could install what I call internal environmental monitoring devices, which is typically called data loggers, or this is sensors. So they can be used to verify the performance of a building when it has been built and compare it to the intention or to the result of this simulations that was used when this design was being done for continuous improvement. In addition to these objective measurements, occupants are valuable sources of understanding whether a building has good or poor IEQ. And this could be done through giving them a survey or maybe an on-site visit where you have a chat with them to find out how hot, how warm, how cold, how bright, how dark is that space. They are a very useful source of assessing the performance of this building, being that they spend the most amount of time in that space than any other person. Different countries have set design goal thresholds for verifying IEQ at the design stage. The table shows a high level, this is summary of the design goals for schools. And we can see a threshold of 300 to 2,000 lux for lighting, where if you go above 2,000 lux, that is the start of a potential issues of glare, being that the light may be too bright to carry out a visual task. And we've got the adaptive comfort threshold of 18 to 25 degrees for the thermal distant performance. And for sound in spaces that are not being used, the background noise when carrying out this design, the target goal should be at least less than 45 decibels. And when the space is being used, not more than 70. And the WHO standards for air quality using CO2 as a proxy for the effectiveness of ventilation is for CO2 levels to be less than 800 parts per million. The next table shows the tools. There are a range of digital tools, which I will talk through some in the next few slides, that can be used to verify whether a design complies with the IEQ standards. We've got, you could use some rules of thumbs for lighting, and you could use the climate-based modeling that uses the local, weather files to assess whether the building will meet the daylight thresholds that has been set. For acoustics, you could carry out an acoustics analysis. And for air quality, you could also use the rules of thumb. Some countries, they've got, I think, a window opening ratio of about 10% of the floor area as a rule of thumb. And you could also carry out a CO2 modeling to assess whether that space is going to have good or poor ventilation. Some of the common tools is, one of them is the IES. It could be used to run a climate-based modeling, and the IES software could be used to graphically display the radiance results of the images to calculate the various daylight metrics, and also to ascertain whether a space will be prone to glare issues or not. Another useful tool is the DIVA for Rhino. DIVA was developed by the Graduate School of Design at Harvard University. It can be integrated with Grasshopper for parametric optimizations and includes an energy simulation component as well. You can see here the various things that could be done with this tool, and we have it. You could use it to calculate your thermal loads. The Grasshopper extension for Rhinoceros can also be used to create the model and perform the DIVA simulations. Another simple and useful tool is the Dynamic Daylight web app. It is a freely available online tool, and it can be used on your tablet and on your phone to explore some of the things we've just gone through in the previous slides. I was thinking of doing a live simulation, but because of time, I may likely skip this. But if you click on the link, or if you go on Google and you Google the Dynamic Daylight web tool, if I click on this, I think it should take us to the tool. It's just popping up on my screen, and I'm just going to bring that up here. And you could just go to the launch app in a new tab. I suspect it should work out. Let's see, and boom, there you go. So you have the tool where you could play with it. You could add more windows, or you reduce the size of the windows or thereabout. Is basically a simple tool that is self-explanatory. And you could run your simulations. For example, we want to run a useful daylight analysis, and we put that in. It's possible for us to choose what thresholds we want, and you could run a calculation. I'm not going to spend much time on this, but feel free to hit on the link, and then you use this to go to the tool and play with it. Moving on. Besides these tools, data loggers could be installed in buildings during construction to gather long-term environmental data after the building has been built. In the past, we usually have devices that measure CO2, that measure sound, measure temperature and light. But in recent years, there is an emerging technology of combining multiple environmental sensors into a single device that could have a robust capability to measure up to 5 different IEQ variables simultaneously. This type of devices are referred to as a multivariable sensor. They may likely be cost-effective and will minimize the use of individual sensors to carry out these IEQ monitoring. These environmental sensors could be used for the belt verification. In the slides prior to this, we have showed the tools that could be used in this design phase. But after the building has been built, you could now use these sensors to carry out a post-occupancy evaluation in conjunction with the feedback from those who use that space to assess whether the building has good or poor IEQ and what improvements could be made if the IEQ levels are below what was expected from the design phase. This is an example of how the IEQ data could be visualized, where it's possible for us to see, this is a graph showing a range of rooms where we've installed our data loggers. For example, we have room 11, room 9, room 10, and we've put the scale of our thresholds, saying we are looking for the good spot, the sweet spot, to be 300 to 2,000 lux. And it's possible for us to see that most of the rooms sit within this sweet spot for during the period of the day. And where we have very high levels, that you can see is the sensor that we had outside of the space, which is more like tracking the outdoor light, these levels. But then we could see in this graph that room 11S has some spikes in the lighting levels at a point in time. So these are ways where we could actually visualize the data that is gotten from the sensors to inform whether a space has good or poor IEQ. Moving on. We know very well that BIM is widely used as a tool for planning, for designing, and also for constructing our buildings. But it can also span into the operation and the management of buildings using data that building owners will have access to. I call it the life cycle, this management of built assets, because it can also provide insights into existing belts for renovation projects. You could use the BIM model of your design to identify what wall the sensor, the data logger, should be placed in towards the end of the construction phase. And you could install this in at scale, and it could provide a useful data to tie back to the BIM model, which could help facility and property owners to make informed decisions about their buildings after it has been built. From a desktop condition assessment of 3D imageries, you can also use IEQ data to provide more insight on the condition of a building. For example, if a roof is leaking, the temperature and humidity levels may not be within the acceptable threshold, as was shown in some slides of the standard thresholds for assessing IEQ. Retrofitting it into a BIM model and using a 3D imagery could provide understanding of the context of a room, and one could even measure the length, the height, and the width of the room. You could use this to measure the different dimensions of the room, and you could locate where you have doors and windows, and you could insert this into a geo model to locate buildings in a large property portfolio. You could merge the 3D imagery with data, which is BIM Light, update information into the hierarchy of the various elements to repurpose and remodel and also retrofit existing belts. 3D imagery provides more data for more informed decision making. It could be used to inform the right location and placement of the sensors and the context of the room. Data from the sensors could be tied into a GIS model, and it could thereafter be used to forecast external temperature levels, the humidity levels, the sunlight, the floodplains, the wind movement. Generally, these tools could provide hard data for a mature and a robust asset management information tool. Moving on to thermographic analysis. Thermographic analysis is the use of an infrared camera to take thermal images of a surface of an object. The thermal camera is a device calibrated to measure the radiation emitted from surfaces. The thermal camera turns the emission pattern of an object into a visible image. The result of a measurement is a thermal picture of the surface in which the different colors of shades of gray and red correspond to the various temperature levels of the target surface. I will wrap up very briefly on the overall importance of monitoring IEQ, linking it back to the design phase and also post-belt. One of it is likely going to help those who use the space to prompt them to be able to control the space for it to function the way the space was intended to function. It will help to provide trends and patterns reflecting on the graphs we saw. It's possible for you to gather long-term IEQ data on the trends and patterns over weeks and months and years to make more informed decisions on what is working well or what doesn't work well in a building or room. It provides a basis for you to assess a space against the building code. For example, the IES tool could help you in the early stages of doing your sketches, where you've sketched your windows, your doors, and the rest. You could put it into the model to test, would this building have good day lighting? Would this building have good cross flow of air for adequate ventilation? It also provides insights. Maybe post-belt, you've been able to use the tools to assess your building and you find out that there is an aspect of IEQ that is not performing well. You could now use the data retrieved from the IEQ monitoring tools to be able to inform you on, oh, do you need to maybe put in a thermal intervention on the walls or on the roofs, or do you need to reduce the size of the glazing, or do you need to add more shadings or not? And it can be used for post-occupancy evaluations to ascertain whether a building or a room has achieved the desired IEQ levels. Besides designing for IEQ, commissioning and handing over training to users is also an important factor to consider when you want to achieve good IEQ. Remembering that users play an important role to ensure that their buildings are operating the way it was intended to operate, such as turning on the heaters when it is too cold and switching it off when it is too warm, opening the windows when the air quality is poor and may have been flagged by the CO2 monitor, identifying the sources of noise and addressing it, and generally ensuring that the indoor environment is conducive for their well-being, for their comfort, and for their health. I will be wrapping up here by saying, in summary, in this seminar, what we have covered is that IEQ has been shown to have a significant impact on the health, on the learning, on the performance of those who use a building. It doesn't matter if it's a home, if it is a school building, if it is an office building, it has been shown to have a significant impact on the users. When a building has been built, IEQ elements have the greatest impact on those who use that space. But at the early stages of doing our designs and drawings, architects have not considered it to be an important thing to think about at these stages, which is why there is need for us to continue to pass on the message saying, when you've done your design, it's a very beautiful design, the building looks awesome, but then in reality, when the building has been built, it may be too warm for those who use it. It may be too cold. It may be too bright, and this impedes on the functions of that space. This makes it important for architects and engineers to effectively consider IEQ at the early stages of doing this design. What I have put here is a sketch that shows the relationship. So when you're doing this design, whether the orientation of the building or the form of this building, you see the building plays a key role in whether the IEQ is going to be good or poor. And we have all the factors. They are all linked. And it ties back to the users of that space. So as an architect or as an engineer, when you're doing a design and you're trying to design for IEQ, you don't only think about the building, but you also think about the factors, how the sun passes in and around a building, and how the wind passes in and through a building, and how it is being felt by those who use that building, and what are the functions of that building, as well as commissioning to ensure that those who use that space can make use of the tools in that space to improve and enhance IEQ at the build stages. I will like to conclude by saying that when designing buildings for IEQ, we need to consider the elements, the 4 elements holistically, because a change in one factor could have an impact on the other.